Hello student, today I am going to teach you about the asymptotic notations. These asymptotic notations are the basics that are used to define and measure the complexity of the algorithms. In this, what we do in asymptotic notations, there are five types of notations. So we shall study one by one each of them. First of all, the asymptotic complexity, running time of an algorithm as a function of input size n for large value of n. Well, actually, the running time of the algorithm is measured as in terms of the n, which is the number of the inputs, is called the complexity because the complexity depends upon the size of the input data, and it is expressed using only the highest order term in the expression for the exact running time. And we do not measure algorithm in exact way. Like suppose we are not saying that the car is running at speed 49.67 kilometer per hour, but we can say that around 49 to 50 kilometer speed, right? 50 kilometer speed. So here we terms different types of notation that shows the limits, which are different types of limit, lower limit, upper limit, and these are called the asymptotes because asymptotes are the curve that passes through the curve but do not intersect with the curves. Now there are five types of asymptotic notations: the theta notation, omega notation, big O notation, small o notation, small o, little omega notation. For example, for a defined set of function in practice used to compare two functions. On basis of these, we can compare that which one of these function is more complex in comparison to the another one. In this, there are different situations in which we use different types of notations. The notation describes different rate of growth relation between the defining function and the defined set of function. Actually, we to measure the complexity, we bound a certain function by another function, and these functions works as the limit of the function, and they fix the limit for that function. First of all, I shall tell you about the theta notation. Suppose there is a function gn, and then the theta gn for the, or this is called the theta gn for the number n is equals to such that as shown in the graph. Here fn is the graph, and it is bounded by the two functions c1gn and c2gn by lower. It is bounded from the lower side, bottom side by the C1gn, and from the upper side by the C2gn. There is a number n0 after which you can clearly say that after that the C2gn function clearly lead or exceed the function fn, and after n0 c1 fn function clearly exceeds the c1gn function, because before n0 the behavior is little bit complicated. So for defining that after the point the two functions show the clear increasing or decreasing pattern with respect to each other is considered as the limiting point. For example, we have defined this function relation between function fn and gn with help of two constants c1, c2 and the n0 variable. For every time n is greater than n0, clearly gn function exceeds the function fn if multiplied by constant c2. Similarly, for every time when n is greater than n0, the same gn function is superseded by the function fn when multiplied by a constant c1 c1. So this function is bounded on both sides by the function gn. We can say that fn is bounded by the both function gn, but just a constant with constant c1 and c2. So this is very tight bound, and this function is very much similar to the function fn, and this is called the asymptotically tight bound. So here in this case we can say that gn is the function that for n0 greater than n, because before after that gn tied or limit the function fn from both upper side and lower side, or it will say that it is a asymptotically tight bound. Here we can say that for Fn lies in between C1Gn and C2Gn for n greater than n0 notation. So Fn and Gn are non-negative and for large number. So okay, this is called the theta notation. It bounds the function from both sides, right? The next notation that we are going to, for example, the theta notation, take the example of 10n square minus 3n. What constant for n0 will work? C1 is a little smaller than the leading coefficient and C2 is little bigger, right? To compare the order of both, look at the leading terms, right? Because in this function we compare the leading terms to basically determine that what will be the complexity of that function, because in the given function 10n square minus 3n, the increase or growth of the function n is very much less in comparison to n square. We can clearly see that because the n square will grow with 1, 4, 9, 16 in a very speedy way or very steeply, but the n will increase 1, 2, 3, 4. So clearly the function complexity will be dominated by the n square function, so it is bounded by the n square function. Similarly, the function n square by 2 minus 3n, here the clearly will be lead by the n square terms, so it is also bounded by the theta n square, right? So this can be bounded by the theta n square function by just multiplying a simple constant c1 and c2. But we can it does not mean that we can bound in any way. It is I have told you about the closed bound that can bound from bottom side and upper side both, but you cannot say that the n cube is bounded by n raised to the power 4, because there will be large gap. There should not be huge gap in between these two. So we cannot say that 2 raised to 2n is bounded by the 2 raised to the power n. So this will be irrelevant, because there is a huge, if there is a large gap in between the function, they cannot be said to be the limit. They should be very close to each other. For that, if you are not getting a function that is very tight, closing the functions from both sides, then we use the function big O notations. In big O notations, when you have not any function that can bound the function from both sides, you opt for the big O notation, in which you create a function gn that after a value n greater than n0 clearly exceed the function fn. It is called the upper bound also. So gn is called the asymptotic upper bound for the fn. Here fn is the upper limit for the function. So theta gn is a subset of ogn, we can say so, because theta lies very close to the function, but the big O notations is a little bit off limit or little bit far from the function. So that will be called as the upper bound function. But we are interested in the nearby limit that exceed the function. For example, linear function an plus b is on square, because definitely the an plus b is a linear function that depends upon the growth of the n, and it is surely smaller than the growth of the function n square, so it is upper bounded by the n square function. Similarly, 3n cube is upper bounded by the n raised to 4 function. The next notation is the omega notation. The notation, in this notations, this is called the big omega notation. After that, I shall tell you about the little omega notation also. In big omega notations, there is it is inverse of the big O notation. It bounds the function fn from the lower limit side. It is the lower bound, and it is here the gn function is an asymptotic lower bound for the function fn. So here we can say that the theta gn is subset of omega gn also, because theta gn binds from the both upper side and lower side, but big omega notations bounds the function from the lower side only. So this function bound theta notation bound the function from the lower side, and the big O notation bound the function from the upper side, and theta and bind from the function from the both sides. For example, under root is the lower bounded by the function log n. because we can see that the under root function is lower bounded by the function log n. Yes, because the growth of the under root n would be, after a number keep on increasing, under root n will decrease much faster than the value of the log n. So log n log n would be always less than the value of under root n. So after a point, sorry, this is the lower bound. The next function is next function is the comparative analysis of these three. Here the three functions, by taking a look of all these three functions, we can say that the function fn is tightly bounded by the upper and lower side by the function theta, and it is upper bounded by the function big O and the lower bounded by the function omega. What is the relation between these three? For any two function gn and fn, if fn is theta bounded by the gn if and only if f is upper bounded by the gn and f is lower bounded by the gn. So if a function is theta bounded by function gn, then it is also bounded by the big O of gn and the big omega of the gn. So in short, we can say that the theta gn is equals to big O gn intersection big omega gn. In practically, asymptotically tight bounds are obtained from the asymptotic upper and lower bounds. The running time. The running time when a function is bounded by the upper bound, it is called the worst case. Basically, the big O notation is used to bound the worst case scenario, and big O of fn is bounded on the worst case running time. And theta fn is the average time. Normally, the theta fn represents that for average case. Most of the time, it's used for the average case. And big O notation of a function is the best case. So big O is the worst case, theta is the average case, and the big omega is the best case. So we can say that the case as it. For example, the insertion sort, the complexity is theta n square in the worst case. But there are some situations in which we can't say these things exactly, because any sorting algorithm must take at each time. So, but in best cases, it is the omega n, means the best case. But in average case, in fact, using the merge sort sorting is theta n log n in the worst case. And in case of merge sort, the complexity is n log n, because it is tight bound, upper bounded and lower bounded, means it is very balanced algorithm, and merge sort shows the n log n because upper bounded and lower bounded because it is theta bounded. Okay. The asymptotic notations. Can use the asymptotic notation to replace the expression containing lower order terms. For example, there is a function 4n cube plus 3n square plus 2n plus 1. Then this function 2n plus 1 is bounded by the theta of n, because the only variable term here is n, so this is theta bounded. And the next term between 3n square and theta n, the n square will dominate, so this is theta of n square. And finally, between 4n cube and theta of n square, it is bounded by the theta of n cube. So basically, the most dominant term and the term that exceed at much higher rate determines the complexity, and used for the asymptotic. According to that, the asymptotic notation is used. So in case, for example, the same 3n square plus 2n plus 1, the complexity would be theta of n square. For a given function gn, the set little o. Now the notation, we have studied the function theta Gn, Fn, and big O notation. Now there are two other notations that are the little O notation, and we have studied the big O notation. Now it is the definition of little O notation. Little o of Gn is such that for n0 greater than 0, that function Fn is lies between 0 and Cgn. Fn becomes insignificant relative to Gn as n approaches infinity. Means the Fn upon Gn with increasing value of infinity becomes equals to 0. Gn is an upper bound for Fn that is not asymptotically tight bound. What is the difference in definition? Because it is also actually it is also the upper bound, but the difference is that this is much closer to that, because here for increasing value of n, the limit Fn upon Gn becomes equals to, this will become in for infinite number, the function becomes so close that they tends to 0, means for increasing value of infinity the Gn function becomes much greater than Fn, and so it becomes infinity. So it is so Fn becomes insignificant to Gn as n approaches infinity. Means Gn functions becomes much dominant than the function Gn for n greater for very large value of n. So Gn is an upper bound for Fn that is not asymptotically tight. Okay, so the little omega notation. The little omega notation shows the same behavior. Fn becomes when n becomes very large, then the limit between n tends to Fn upon Gn. In the last function it was Fn upon Gn. Here the same function is, which means the Gn functions becomes very large for the n value, that this term's limit n tends to infinity, Fn upon Gn becomes infinity, and Gn is the lower bound for Fn, and that is not asymptotically tight. Here the term, when a function is not, there is no asymptotically tight bound, then we find out the lower bound in case, right? Comparison of the function. For example, the f and g, the when Fn is the upper bound of the function Gn, then suppose there is a variable a in f and corresponding there is a b, then definitely what will happen, the function Gn would be greater than or equals to the function a b, and in case Fn is the lower bounded by the function Gn, then for Fn there is a variable a, then a would be, the Fn would be greater than the or equals to b, right? And in case Fn is theta bounded by Gn, in case a is equals to b, means both will be nearby equal. And when Fn is little o of Gn, then in that situation what is happening, Fn is less than b but not equals to that, it is definitely less than b, and it is clear cut, it is definitely close than that function. And when Fn is omega bounded of Gn, then a is greater than b, there is no equal signs, means Fn always less than Gn, and in this little omega notation Fn is always greater than Gn, right? So now there are certain limit, when limit Fn upon Gn is equals to 0, in case of in both case when in Fn upon Gn is equals to 0 in case of little o notations, but limit n tends to infinity, Fn upon Gn is less than infinity, because the Fn function is less than infinity for Fn big O of Gn, and in case of the limit n tends to infinity, Fn upon Gn is less than infinity for theta bound, when Fn theta bounds the function Gn bounded by the Gn, and in case limit Fn upon Gn tends to infinity, Fn is little omega of Gn bounded by that. Okay, and when Fn upon Gn is equals to infinity, for Fn big omega, little omega of Gn, and limit n tends to infinity, and Fn upon Gn is undefined, can't say. There are certain properties associated with these. Just take a look of that. It means if a function Fn bounds or Fn Gn bound the function, then what happens? The one function bounds the Fn is bounded by some function Gn in some notation, and the function which was which is bounding is bounded by some another function. Then there will be transitive. Means if Fn is bounded by Gn and Gn is bounded by Hn, then Hn will be bound the function Fn. That's called the transitivity. And reflexivity means each function bound itself. Symmetry. A function is bounded by Gn, then the same function can bound the function in a symmetric way. And it is also complementary. It means if a function Fn is upper bound by the Gn function, if Gn is lower bounded by the big omega, big omega of Fn, and Fn is little o of Gn, then Gn is omega of Fn. Some common functions. These are the if M is definitely, these are very simple things. Just take a look of that. Okay, these are very simple things. These are the some normal identities which you should know before solving the complexity, deriving the complexity of the function, and the basic thumb of the basics of the log. One of them, these are the basics that you must know before solving the. So just take a look of that. If the base of the logarithm is changed from one constant to another constant, the value is altered by the constant factor. This is the simple thing. For example, log 10 n base 10 into log 10 base 2. If we multiply these two, then this would be equals to log n base 2. Okay, this is the one of very useful thing, and you should know that. Exponential with the different thing. And log of n factorial is equals to theta of n log n. Okay, so this is the one of the few rules that you should know. And here are the exercise questions. So, and there are these two functions 5n square plus 100n and 3n square plus n. A is definitely a subset of theta gn, or a is theta bounded by the gn. Similarly, the log base n square base 3 and log n cube base 2. Here we shall use the concept of the log, and by using these concepts we can say that this is equals to 2 log n base 3, and here this is equals to 2 log n base 2. B is equal, so the function b is equals to 3 log n, and the function a is equals to 2 log n upon log base 3. A by d, comparing these two functions, simply a divided by is equals to 2 upon 3 log 3. So clearly that would be, this function is less than 1, so we can say that the A is theta bounded by the B. In n raised to the power log 4 and 3 raised to the power log n, we can say that A by B is equals to log n 4 by 3, because dividing these two, we can say that n raised to the power log 3, and 3 log n can be written as n raised to the power log 3, and log 4 upon log 3 is equal to log 4 by 3, n raised to the power 4 by 3, so that would be infinity, so it is omega bounded. Okay, so the solution, so that's all I want to complete. So that's all about this. So thank you for joining.